Right, we had a look at part one of topic one in P2, but now we're going to have a look at part two, and part two is about electric current. Current is something that flows like the flow of water, current in a river, and you need to know how we describe it in physics. So the first thing is that we need to know a little bit about metallic bonding, which you do in C2 in chemistry, and you know that in um, metals. So let's say we've got a solid piece of copper wire. Right, so I was just talking about, sorry I was interrupted, atoms in a solid, so they can't move past each other, and however in metals there are these delocalized free electrons, and without there being anything connected in terms of a source of potential difference, something that supplies energy in a circuit such as a battery, these electrons will just kind of aimlessly wander around in different directions, no particular place to go. However, if you then attach, and I'm going to zoom out again now, and so we just draw this wire as one thin line. If we then have a little wire here, and going to say that the electrons will be attracted to, now this is a bit odd, I can never remember which way it goes. This is negative and this is positive. So we would normally say that the electrons would be attracted, negative electrons would be attracted in this sort of direction. And so that this battery contains, for instance, it might just contain 2 plates of metal and an acid. In any case, what you need to know is that it draws the electrons in a particular direction, and that means that electrons need to be replaced, and so they leave the battery, and can we get a flow, a circuit of flowing electrons, and these electrons have a charge. So charge is being carried around the circuit, and across here we have what is called a potential difference, or the common way of saying that is voltage, and this relates to the amount of energy, the energy difference between the electrons that come in and the electrons that leave. And that energy can be used in components. So for instance, if we do the very simple circuit of a cell with a bulb, then the electrons that go into the battery might have hardly any energy. The electrons that leave the battery will have lots of energy. Let's say we've got 6 volts of potential difference, then all 6 volts will be delivered to the bulb here. In fact, if we put 2 bulbs in a parallel circuit, I'm going to draw it like this now, parallel circuit, then each electron that goes to each bulb will have 6 volts going in and 0 volts going out, because each electron, no matter which way it goes, will just go through one bulb, so the bulb gets all the energy. However, if we have a series circuit, and we'll still have 6 volts here with 2 bulbs, and this time we've got a series circuit has just got one loop, then each bulb has to share the voltage, because every single electron has got to go through here, over there, through there, over there, and its energy is shared across the bulbs. So there's a difference here between series circuits and parallel circuits. What we can say is that the voltage might be, for instance, if we measure the voltage across here, we measure voltage in parallel, so voltage around that bulb would be measured at approximately 3 volts. The voltage around that bulb would be measured at approximately 3 volts, and the voltage around that power supply would be measured at 6 volts. What we can say in a series circuit is that the currents, I'm just going to make a number up now and call it 2, and we measure current in a unit called amps. The current is the same. Wherever it is in the same loop, it's the same. So the current kind of tells us the speed of charge. So you'll see in your formula sheets a formula like that. Q, strangely, it stands for charge, and I, even stranger, stands for current, and T, not so strangely, time. Now if you're given some numbers and you're not sure how to rearrange those equations, you can just put Q there, I there, and T there, and cover the one up that you want to work out. So T is Q divided by I, Q is I times by T, and I is Q divided by T. So we've got an idea of current is charge. Charge is current multiplied by time. And you will also need to know a little bit about voltage, and so we can talk about voltage or potential difference. So I was talking about voltage, and you need to describe voltage in terms of being the amount of energy that each charge carries. So in a similar way to Q, I, and T, you might find this a way of working it out. So if you want to work out Q, it's E divided by V. If you want to work out E, it's V times by Q. So we've got volts. E, energy, is measured in joules, and Q is charge, measured in coulombs. You'll see that again in your formula book. What else do you need to know? You need to know a little bit about resistance. Now, resistance is the difficulty or ease with which charges can move through something. So let's say this was gold. Now the charges can move really easily through gold. Gold is a really good conductor. The only reason we don't use it for wires is because it's so expensive, but great conductor. And so because it's such a good conductor, we say it's got a low resistance. If things were a poor conductor, they still let electrons flow, but the electrons find it hard work. And we can actually put these two equations sort of together, because resistance is an idea of how quickly the charges, the electrons, can move through, but also how much energy, how hard it is for them. So there's 1/3 equation which talks about the voltage or potential difference V equal to I, the current, multiplied by R, the resistance. Now in terms of units, we've got volts here, amps for current, and resistance is measured in ohms, O-H-M, ohms. And again, you might need to do some calculations where V, I, R, so you could rearrange, to work out R. R is V divided by I, and so forth. I is V divided by R. I think we'll leave it there for now. I might just have a little go at components in the next section.